All right, hello. My name is Cameron Kirk, and welcome back to my tutorial series on the DE10 Nano. This is video number 3, and today what I'd like to do is, before we start getting into writing Verilog code and seeing how that works, I think it'd be a good starting point for us to do a project using the block diagrams. And this is going to give you a real visual idea of what exactly it is you're going to be programming in Verilog, at least for combinational circuits. So yeah, I'd say the best way to start is to do combinational circuits first, and we'll do it on the block diagram. And so it's like we're going to be working with pictures, and it's going to be a really nice introduction into writing the exact same, creating the exact same circuits in Verilog. So let's get started with creating a new project. I think this will be a short video. Okay, so we're going to click next, and if you didn't see my last video, if you're not sure how to go through this new project wizard on Quartus, the best source of instructions that I found were shoot, I didn't have my browsers ready to go. It was on the GitHub repository that has the write-up for my first FPGA. Let's see, I think I have this GitHub link right here. No, is it this one? Let me see here, pull up my notes. The link will be in the description. I just want to show you where I'm getting this from. This one. Okay, click that link. And it's loading. Now I need to pull this up where you can see it. Here it is. So this is you can see the GitHub repository right here. If you go into tutorials and you go into, we want to do the My First FPGA, but don't go in the folder. You have to scroll down and download the PDF write-up here. I already have this downloaded. So let me open up File Explorer and navigate to that folder, DE10 Nano. And this is going to be in my live demos. No, not live demos. This is going to be in my repos folder because it's a repository. There it is. And I already have it downloaded, and I put the corresponding PDF in the corresponding folder. So this write-up here has the instructions for how to create a new project, which is important. The only important part is selecting the device. So I'll just kind of scroll through here. Create a new project, yep. Give it a name, give it a folder. So let's go ahead and do that. I am going to do this in my live demos folder. So I'm going to go back to documents, DE10 Nano, live demos, new folder. This is vid3. Okay, select the folder, select the folder. All right, name of this project, we're going to call this _block. You can name yours whatever you like, but the name that you pick, you have to stay consistent throughout your design. The project name has to match your top level entity of your design file. You're not really going to see where that comes in this video because we're just going to have one design file, but all the names have to match. As you start doing more complicated Verilog designs, you might have second and third Verilog codes that you're bringing into the main top level entity because, yeah, again, this is a hierarchy, and a hierarchy is like, the parent-child relationship and so on. Anyways, so I'm going to call mine _block, and I'm going to stay consistent with that naming throughout this project once I've picked my project name. Okay, we're doing an empty project. I'm going to speed up along here, go a little bit faster. This is the part where I would like to refer to this PDF because I don't have this memorized. Doing Cyclone 5 SE base, Cyclone 5 SE base, and there's the device name. This is for the DE10 Nano, CSEBAU623I7. See if I can do this on the first try. Need to see the full names here. 23I, is that the one? CSEBA6U BA6U23I7. That's the one. Okay, so I have that selected. I'll click next. We're gonna be using the defaults for all of this, so don't change anything. Click next. And I know that because that's what the instructions said down here, since we're not doing anything. Again, this is a really good guide for setting up a Quartus project. Because I'm used to Quartus 2, and this is Quartus Prime, and there's a couple of things that are different in this project wizard. So that was nice to know how to get through all those screens. Okay, we're all done. We'll click and finish. Might take a moment. So we're going to be doing the block diagram schematic for describing our circuit. So we're going to be working with, a big, basically just going to be working with pictures. And that's going to be a really nice way of, getting an introduction to what hardware description is all about. Okay. So, sorry, I should slow down and see what I'm doing. I'll go into File, I'll click New. And I'm not going to get a Verilog HDL file. I'm going to do this block diagram schematic file, and I'll click OK. And now that I'm thinking about it, I might do 2 or 3 videos working with this block diagram just to make sure I have time to talk about everything and really get across what we're doing. I'd say the block diagram is helpful and easy to work with for small circuits. As you start to scale up and you make bigger and bigger hardware designs, you're gonna hit a limitation on what you can do working with the pictures. Yeah, and then so we'll stick with this for a couple of videos, and then we'll move on to Verilog. What else did I want to say about this? I don't remember. All right, let's just jump right in. So this is your block diagram. There's nothing here. You want to work with these buttons up here at the top. So we have this button right here. This is the symbol tool, and it looks like an AND gate to me. So as a matter of fact, we want to get an AND gate. So what we want is a 2 input, 1 output AND gate. And so basically the idea, it's easier to just show you. This window popped up when I clicked that symbol tool, and down here on the name, I'm going to type in and push enter. And it can't find it, but that's okay. There should definitely be an AND gate in here. Maybe I'll type less. What is it, an AND 2? AND 2. Oh, there it is. Oh, that went too fast. Then it popped up when I said AND 2. So it's under, so you drop down this folder. Oh my goodness, come on, work with me. You'll drop down this folder, and then under primitives, under logic, we're going to be doing the AND gate. So there's an AND 12, and what that means is it's an AND gate with 12 inputs. We're going to do an AND 2, so 2 inputs, 1 output. And what this logic symbol is basically saying, and by the way, all AND gates are drawn with this flat side, and that's where the inputs are coming in, and then you kind of have this round letter D shape. Yeah, that's an AND gate. That's always going to be an AND gate. Anytime you see that in a diagram, that's an AND gate. And you have 2 inputs and 1 output. And you can think of these 2 lines here. They are literally like physical wires that carry a physical signal. And that signal can be either a logical 1 or a logical 0, 5 volts or 0 volts. So imagine you have, I don't know if you have any experience with electrical engineering, but basically you have these 2 wires, and they're both connected to ground. There's no electricity running down them, and you decide to connect one to electricity and the other one not. The other one is just still connected to ground. There's no electricity flowing through it. There will be no electricity flowing out on the output. And then same thing if you turn this one off and you turn the electricity on for this one. There is no electricity flowing out. It's only when both of these guys are going to be connected to electricity that we have the output. And it's in the name. You have to have A and B in order to get the output. You have to get both of them flowing. Okay. So I'm going to click OK, and I'm just going to place this down, and I'm going to zoom in on it. think that might be helpful to make this a little bit bigger. So again, I went up here. This window pops up. I select the AND gate. I click OK, and then now my mouse is moving around. You just click and plop it down. It's basically like Legos. I'm going to switch my tool here from the logic symbol tool. I'm going to go back to the selection tool, and that's going to let me click this guy and move it around. So we have this AND gate, and yeah. So let's talk a little bit more about what's going on. These logic gates. So if I do AND logic gate, you can see that I'm not making this up. There's a whole Wikipedia page. Feel free to take a look at the Wikipedia page. I'm sure that there's not going to be incorrect, information on here. I'm sure it'll be fine. Might even learn something. Also, feel free to look up, YouTube video on what this is. It really is so simple, so intuitive to pick up. Don't overthink it. It's just like Lego blocks, and you connect wires, and to that. And the other thing to be aware of is something called the truth table. So this is a truth table. It's showing what your inputs are and all the different possible combinations of inputs that you can supply. So 0, 0, 0, 1, 1, 0, 1, 1. That's every single possible combination you can do, and it shows you every single possible output that can happen. So let's say we're working with a new gate. We're going to be working with the AND gate in this video, but let's say we're going to do the XNOR gate. And you're like, what the heck? That sounds crazy. What does it do? You just type in XNOR, the name of it, and then truth table, and you will see the truth of how this gate works. So we have the XOR and the XNOR. There's the XNOR. X and Y are the inputs. There's every single possible combination. See if I can make this picture bigger. Open image in a new tab, and we will zoom in on that. Every single possible combination of X and Y. And then here is the the equation. If you wanted to learn the Boolean algebra equation, I don't think we'll really get into how to work with that stuff in this series. We're going to be focusing a lot on the Verilog. You don't really need to write by hand Boolean algebra. But that's what this is. This is the equation. So like the multiply sign or the add sign. This, you do a circle with a a plus in the middle of that circle, and that's going to be your XOR. And then if you put this bar across the top of the entire thing, you're basically saying not. Whatever it is, it's going to be the opposite. So you can see regular XOR. This is the output for an XOR. An XOR is exclusive OR. So you're saying I need to have one or the other exclusively. It can't be both. So you can see if we have nothing, our output is no. If we have one, we have a 1. We have 1 exclusively. We have just the Y exclusively. If we have the X, we have the X exclusively, so we have a 1. But if we have both of them, that is not an exclusive OR. We need one or the other, but not both. And we have both, so it's saying false. We're not going to give a green light because, and then, so if you're going to throw a NOR on there, you're just basically throwing a NOT gate. And you'll notice the symbols, the logic symbols, they're basically the same. You just have this little circle in the front. And that circle, anytime you have a gate that you recognize, and then you see a little circle at the tip right before the output, they're basically putting a NOT gate right at the output. So they're flipping the output inside this gate. And so basically it's exactly what the XOR was, but not. So if you have a 0, and that's going to be not a 0. If you have a 1, it's going to be not a 1. So it's just flipping the outputs, but you get the idea. So there's all sorts of gates. I'd say the ones to be aware of, we're doing the AND gate today. AND gate. We're going to see the OR gate. Oops, I should probably say OR gate, gate. So yeah, there's the OR gate. What else do we have? We have the NOT gate. So basically A goes in, and then whatever A is, the output is going to be not that, right? And then there's a NOR gate. Yeah. Let's see. Let me check my notes. Make sure I wrote down a list of them. List of ones. Exclusive OR. We already talked about that. There's the XOR gate. And again, if you want to know what it does, just look up the truth table, and you can see what's going to happen when you use that. The NAND gate. I think the NAND gate is a universal gate. Might be remembering that incorrectly. But yeah, there's the NAND gate. It's an AND gate with a NOT. So it's literally the AND gate, but to put the little circle on there, you know it's going to be exactly the opposite of an AND gate. So you can take a look at that truth table there. That is exactly the opposite of what we had for the AND gate. You want A and B, so you'll give a true, you'll give a 1. Otherwise, it'll be 0. This is just the complete flipped opposite. So that's all an AND gate is. And you know, there's also a NOR gate. I think, did we already see this one? Well, anyways, there it is. So the OR gate is one or the other or both, either or, and you can have both of them and you'll say true, 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 true. But NOR is the exact opposite, so you're just flipping it. So if you have nothing, you'll give a true. And if you have the case, you know, of any of them being on, you'll say false. So these are all like logic, you know, you might see, we already saw the word primitive. These are like, you know, the building blocks for you to start building a circuit that implements, you know, logic. Like you want it to do some processing, and that's really what you know, hardware is all about. Is we want it to do these computations and think about how we're gonna, you know, process information given some inputs. Maybe these inputs are connected to, you know, a security system in your house, and you know, you want the alarm to sound, you want the alarm to not sound if everything is off, but then if any one thing is on, you're going to give a 0, and that 0 is going to trip the alarm, however it's set up down the chain. But you can chain logic together like this, and you can create all sorts of cool stuff. But this is like the basic building block that you're going to build anything out of. And as a matter of fact, the ALU, so let me, before I get into that, there is the CPU, pipeline, and if we take a look in here, this is, so we'll look into this more depth in a much later video, but if you look closely, you will see that there's an ALU in this diagram, and there's an ALU in this diagram. Every CPU has an ALU. There's an ALU, and what an ALU is it is a arithmetic and logic unit. And people like to say that the CPU is the brain of the computer. Well, the ALU is the brain of the CPU. So let's just take a quick look at a ALU block diagram, and we will study this more in another video, and we'll actually build one. Let's see. Yeah, so this is, I don't know, is this actually an ALU? I'm not prepared to actually dig into this. They represent it with this, but there is actually logic gates inside the ALU, and it's actually doing, yeah, this looks like an adder. Oh, that's a full 1-bit adder. Let's just look at an adder block diagram. I have a block diagram in my notes of an ALU, and so we'll look into that in another video, how to actually make the ALU. But again, it's just going to be logic building on top of that. So here's an adder. Here's a this is going to actually allow you to add numbers. So you have a number represented in binary, and then this this setup of logic gates connected to each other actually will add these two numbers together. And this only allows you to do 1 bit, but you'll start to see that you can actually have multiple bits all in binary. This is the logic required to add 2 binary numbers together in a simple adder. And this is definitely a video I'd like to make. I don't know if we'll do it in a block diagram, but this is why it's important to understand what's happening with the block diagrams, because that's ultimately what you're going to be writing in your Verilog code. So this is nothing like programming in C. You need to be thinking about these logic gates, and that's why we're starting with the block diagram. Okay, that's probably enough rambling. Let's get this video going. We'll finish out the project, and then we'll be done for today. So we have this AND gate, and I think technically we could compile this, but this isn't going to do us any good because it's not connected to anything. So when it wants to save, I'll say yes, and you'll notice it's going to type in my project name. This is because we want this design file to be the high-level entity. It needs to match the project name. So I'm going to click save because I do want to use that. It typed it in automatically for me, but I want to use that for this design file. I'll say yes. So now my block diagram is named the same as my project, which is good. So we'll let this compile. I probably shouldn't have started the compilation. I'm going to pause the recording until that's all done. I forgot that takes a couple minutes. Okay, we're back, and it actually didn't compile. It says it's not happy. Top partition does not contain any logic. Yeah, so this is an incomplete design file. I probably shouldn't have clicked compile. Anyways, so what we're missing is we need to actually have a couple of nodes here for inputs and a node for output. And as soon as we add those in, those are actually going to allow us to connect to the actual board itself using pin assignments. If you remember in the last video, we did some pin assignments, and we didn't really get too into depth with it, but we can see on the schematics of the DE10 how to do the pin assignments. But yeah, so let's just jump right in. So I'm going to go back into the symbol tool, and that's going to open up this window. And this time I'm going to type in input. Oh, sorry, we don't get it from here. Cancel. It's not a symbol tool. Inputs are actually right here. So there's the symbol tool, my mouse to the right. There's the pin tool. If I click the little drop down arrow, we can pick an input, and I'm going to drop in a couple of inputs. Oh, I think I'm zoomed in too far. Drop in a couple, and I'm going to switch back to the selection tool. So you'll notice these aren't actually connected to each other, but I can click and, oh, sorry. So if I hover over the tip of this wire right here, you see my cursor has that little line with the two dots. If I click and drag, I can pull out a wire, and then I want to connect it to here, and you see that it draws that box around my crosshair. That means it will connect, but I don't like to draw my wires like that. What I'd like to do instead is kind of just come out this way and line it up so I could go straight in, but it'll only draw one angle on this wire until I let go. So I'll let go, and now this wire is incomplete, but it's stretching out, and then I'll click over here and I'll drag it the rest of the way and connect it. So now it kind of does this snaking, and I think that makes it a lot more organized. Instead of just having one turn, we're doing two turns to get there. Anyways, so I'll click and drag, and I'll come over here, and then I'll connect this guy. And there we go, we just wired him up. And then I have the selection tool selected, so if you're not able to do that, make sure you have the selection tool selected. The pin name, so I want to change the pin name. I'm going to double click on this, and I'm going to type in A. That's input A. Here is input B. Cool, so we just made a signal input A and a signal input B. And we're gonna actually be connecting to these to the, here, let me switch over to the board view, tabletop. On the DE10, my board is not connected yet, but you'll see down here, it comes with switches. If you take a look on your board, we've got some switches. So we're gonna actually connect our inputs to these switches, and those are going to be our input signals. Yeah. Okay, let's switch back to the code. Well, you can call it code. We're going to go back to the symbol. No, not the symbol tool. We're going to go to the pin tool to the right of the symbol tool. Click the drop down. We're going to get an output over here. Super simple. Go back to the selection tool. And on the pin name, I'm going to change mine to... So if you double click it, sometimes the text will highlight and you can just type right there. Other times you might get this window that pops up. I wish I had said that earlier when I did the inputs. I'm sure some of you probably double clicked it and then you had this window pop up. But you can see pin names. I hope you were able to figure that out. I'm gonna do C for my output. And there it is. So I now have an output named C. And then I'm gonna go right here on the tip right here so that my crosshair has that little tool popping up. And I'll click and drag, and I'll connect it to that. And we're done. We just completed our first circuit. Congratulations. Go ahead and Control S to save. And then up here at the top, we're going to do Start Compilation. And I'm going to pause the recording so that it doesn't take too much time. Okay, it's not done compiling yet, but I just realized I made a small mistake. It's complaining that the pins have incomplete I/O assignments. We did not do our pin assignments, and I clicked compile. What I should have done was like what was shown in the My First FPGA project, where you just do the analysis and synthesis step. That's really all you need to make sure that you're making a valid design file before doing your pin assignment. Compilation should have been my last step after doing the pin assignment. But we're gonna have to wait until this is all done. It should be done very quickly. This is a very small design. Okay, I'm gonna pause it again. Okay, we're back. Compilation was not necessary, but as you can see, it was successful. It just had some warnings. So let's get in there and let's do the pin assignments. So I'm gonna go up to Assignments and Pin Planner. And what we would like is we'd like to connect to the switches. Oh, look at that. So we have our A, our B, our C, and they have the inputs and outputs correct, but the location is what we need to figure out how to do. So let's kind of take a look at our board for a second. I'm going to go to the tabletop, and I know this is a more low resolution camera, so you probably can't quite see this, but if you let's see, do I have something for pointing? I'll use I don't have anything for pointing. My fingers are too big to point on this small board. So I'm going to bring it up to the camera. I have this little wire here. If you look very carefully all the way down on the plastic PCB part of the board, in between these switches here, the bottom of the switches and the top of your Arduino GPIO all along here. If you look down in there, and I can't get this on the camera, I can't get a picture of that, but you will see some white text and a very, very small font. And I see that this far left switch right here, holding the board in this orientation, this far left switch, the white text says that is SW3. And then we have SW2, and we have SW1, and we have SW0. So that is good to know. And then the other thing over here, we have our LEDs, and those are like LEDs here. So what we want is, I think I want to do SW0 and SW3. I want A on SW0 and B on SW3, and I would love for C to be on one of the LED outputs. So let's see if we can figure that out. I'm going to show you how I'm going to figure this out live right in front of you so that you can sort of get an understanding of what I'm doing to get this information on my own without looking at a guide. Okay, so first things first, in my previous video I showed some GitHub repositories, one of which was this one, and the link will be in the description if you'd like to go look at this yourself. Let me pull it up. It is the Intel repository, the DE10 nano web content. In the previous video I asked you to clone this repository, so I already have this downloaded, but I recommend cloning it. And what this gives you is the content that you get access to by doing the out-of-box demo that runs the web server using the HPS core and the SD card, the micro SD card that comes with your board. It comes preloaded with an image. It comes preloaded with this code that runs a web server, and you can plug it in and connect to it over USB, blah, 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 blah. You don't need to do that. You can get access to all that content right here by downloading this repository. So here is the repo name. You can go look it up or check the link in the description, or if you already have it, great. I already have this clone, so I'm going to go on my computer into my documents and into my DE10 folder, into my repos folder. There it is, the nano web content. And we're not going to open up the index. We're not going to actually look at this website. We're going to go into assets. This is something I said you should probably save in a more convenient location. I'm just showing you in case if you came to this video and you didn't watch any of the other videos in my series. This is where you can get access to this DE10 nano schematic. This is, one way of getting to this, but you need this schematic file. So I'm going to double click this. I recommend saving this in a more convenient location. So this is what I need to figure out where, what I'm trying to figure out is back on the pin planner, I want to connect A to SW0. So the location, I expand this out, there is no SW0. They all say pin and then they have some code. And then the descriptions are totally not related to what this pin is connected to. So we need to figure out how this pin, what's the pin code for the SW0? That's what we need to figure out. To figure that out, you do it here. That's what this is for. This, you know, this 24-page document full of diagrams is how we're going to figure this out. So I'm going to start flipping through here. This is useless. I mean, maybe it's helpful, but we don't need to look at this. So I'm just going to skim through here. The Cyclone 5 SoC, that is our FPGA. And then you'll start to notice we have these little codes. I'm going to zoom in here. We have these little codes here. Look at this. Y11. If I go back to the pin planner, there is going to be a pin with code Y11. And I don't even have to search. I can, whoopsie, I sorted. I don't have to search. I can type in Y11 and it types in pin for me. I push enter. It's now wired up to Y11, but that is not what we want. That's a GPIO 0D32. We're not using that in this project. We're looking for switch 0. So I'm kind of just scanning alongside these boxes and looking at these. Oh, I see LEDs. I don't think these are the LEDs. Oh, yeah. Here we go. So here's an LED. Here's all the LEDs. So here are all the pin codes for all the LEDs. So 0 through, you know, they're all here. I don't know why those are on that side and these are on this side. Doesn't matter. We have the codes now. So I'm going to get LED 0 because why not? That is a pin W15. So on my output, I'm going to type in W15 and it types in the pin for me automatically. I did not type pin underscore. I just put W15, push enter, and it's done it. Great. So the output is now done. We needed the input still. So we have to find where the switches are. So GPIO, LEDs, no, we don't want GPIO, no. Key 0, key 1, we could use those. Now I just know from memory that key 0, key 1, those are the push buttons. They're tiny, tiny push buttons. But no, what we're after is we're after the switches, and I'm not seeing it on this page. Okay, so I'm not seeing it, but I'm not going to pause the recording. I'm going to do this live in front of you. The information we need is in this PDF somewhere. And I haven't done this before yet. I haven't connected to the switches yet. I'm doing this live in front of you right now, so just bear with me. And the reason why I'm doing this live is because obviously if you have this board, you'd like to do your own project and you'd like to know how to do those projects and not just follow guides. You'd like to be able to do this sort of thing on your own. So I'm showing you this is how it, you know, the sausage is made. You got to look at dumb diagrams like this. Oh, bingo. Here we go. On page number 6, I see SW0. I see them all right here. So let's zoom in on that. I see SW0 is Y24. So I said I wanted A connected to, so we're going to overtype this. I'm going to click that with it highlighted, do Y, oops, no, I got to backspace it. Y24, enter. And there it is. And then same thing for B. I said B, I want it on SW3, W20. I'm so glad we found that. I thought that was going to take much longer than it did. I thought I was going to be flipping through these pages and looking like a fool. Okay, we're good. Now, one thing that I'm not familiar with is this I/O standard, 2.5 volts, and I'm just doing this based on what I saw in the my first FPGA write-up. And I'll even go to the part that I'm referencing. I've never had to do this before. My experience is working with the the DE2, which is a much more expensive board. I had access to that board from my university, but I had to return it after the semester ended, so I don't have access to that board anymore. And I wanted to buy it, but the DE10 Nano was way cheaper, and it looked like everything that I wanted, and I didn't want to drop, you know, $600 on a development kit when I could do it the exact same stuff, you know, for $100. And when I used the DE2, I never once made a design that it needed something bigger than the DE2. I felt like there was a lot of what are they called? logic units. I don't know, but when I would load my designs onto the board, I think it says it in the output down here. It says like how many LUs you use. Yeah, this right here. So it tells you the total pins, the total logic utilization. I'm using, in this design, I'm using 1 out of 41,000. And then on the DE2, I think there's even more, there's even more hardware available to use, and I never come close to using all of it. So I figured, I can get a smaller board and still do what I like to do. And if I ever come to the point where I max out the FPGA on the DE10 Nano, I think that's good. That means I'm getting pretty good at this stuff. Anyways, let's get back on track. So I'm just following the write-up My First FPGA. They say we want to do 3.3V LV TTL on the IO standard. So let's just do what that does. I don't even know what this is changing. I mean, obviously it's changing some sort of voltage, but that is beyond my pay grade. So I don't know, whatever. Great. So you just close this out, and we'll do a compile. Right? We'll do a compile. Let me check my notes. Yep. Oh, well, there was one other thing I wanted to do. I'm going to pause the recording, wait for this compiling to be done. It is good to compile, so you can go ahead and compile, and we'll be ready to program the board. But there is one little detour I wanted to do before we program the board that may seem trivial right now, but as your designs get bigger, it is nice to do what I'm going to show you. And yeah, okay, let's pause it. Okay, welcome back. So at this point, we are ready to program the board, but one little detour I wanted to make, and I just wanted to show this to you. This is really fast. I'm going to go to File, New. I'm going to add a new file to this project, and I'm going to add the one that is called, if you scroll down, under Verification Debugging. This is sort of a debugging step before you actually load it onto your board. This is a better way of making sure your circuits work before you bother putting it on your board. And that it's gonna basically let you find where your code is going wrong or whatever it might be. Anyways, we're getting this university program VWF, which I think is like vector waveform file. I think that's what the VWF stands for. But the university program, we're gonna get that. Click OK. Opens up this new window, and what this is it's gonna plot our signals, and you can test out your circuit this way. This is one way of testing your design, so without actually putting it on the board. So in this area over here, there's nothing here. You're going to right click, you're going to do insert node or bus. A new window is going to pop up. It's popping up on my primary display. I have to drag it up to the secondary display, and then you get this weird thing. Just ignore it. Click on node finder. Another window pops up, and leave everything default. Just click list, and boom, there's all our stuff. Click the greater than sign, moves it all over there. Click OK, and boom, there is our inputs. Now here is the trick I like to do. What I want is on the inputs, I want to test every possible combination of inputs that are possible. And you can do it this way. You can highlight a section, and then you can click this high button, and then this just makes a big mess. You can do a 1. Yeah, you want to do a 1. This is a terrible way of doing it. It takes so long. An easy way is select A, apply a clock to that signal, or a count. I guess it says count. I thought that C stood for clock. But anyways, transition occurs every 10. So every 10 nanoseconds. If you really are doing some crazy designs, you want to get down to the micro, or what's big, what's smaller, nano? Nano is smaller, right? 10 to the negative 9. Yeah, nano is smaller. I'll do micro. Yeah. 10 to the negative 6 for micro. Yeah. Okay, so yeah, but leave this at 10. Just leave it all default. I'll do micro, it doesn't matter. Click OK. Okay. I'll do nano. Every 10 nanoseconds, we're gonna toggle A. Click OK. I don't know why it complained to me. And that's looking a little bit too small. I don't want to see that many little changes. So I'm actually going to put this at 100 nanoseconds. And then on B, apply a count. I thought it was clock, but I guess it's count. And we're going to do a transition every 200 nanoseconds. We'll click OK. If you have, and so now you notice we have a section where both are off. We have a section where there's only A. There's a section where there's only B. And there's a section where they're both on, and then it repeats. This is such an easy way to get every possible combination. And if you have, let's say you have a third input and you want to do that one, you're going to be doing powers of 2. So let's get the calculator out for your times. I've done this so many times that it's pretty straightforward. What happened to my calculator? I can't use the calculator. There it is. So your first one is going to be 1, or I guess 100. Your second one is going to be 200, and your third one is going to be 400, not times. And your next one is going to be 800, and your next one is going to be 1600. Oops, 1600. Anyways, 1, 2, 4, 8, 16, 32. If you don't recognize this pattern, what I'm doing is I'm taking 2 to the power of 0. Okay, let's go to the scientific. This is binary, by the way. Yeah, this is like just straight up binary. We're going to do 2 to the power of 0. That's going to give you 1. And then we're going to do 2 to the power of 1, which is 2, or 200. And then we're going to do 2 to the power of 2, which is 4. And we're going to do 2 to the power of 3, which is 8, and so on. I say this is binary because if I go to the programmer and I do 1, that is going to be 0, 0, 0, 1. If I do 2, there it is. If I do 3, oh no, we're not doing 3, we're doing 4. There it is. If I do 8, there it is. So I would spend some time, look up some videos on learning binary. Definitely. I'll try to show some stuff. But basically what this is showing is that if you have this bit on, it's equivalent to 2 to the power of 4. This one is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. My mistake, not 2 to the power of 4. So each position is 2 to the power. It's kind of like in our number system, the one that you learn in school. You have the ones place, the tens place, the hundreds place, the thousands place. But in binary, it's the ones place still. And then we have the twos place. So if you have a 1 here, that means you have a 2. And then you have the fours place and you have the eights place. Yeah, check out some videos in binary. I'm not going to spend too much time here. Anyways, so we got this waveform. And we're basically applying these signals to the inputs. We want to see what the output looks like. So you click this little play button up here and you save it, yes. And then we'll save it. And then it runs its calculations. So generating a test bench, and it's basically going to simulate your circuit and make sure it'll simulate what your output's going to be. So if you have like really complicated logic, this will show you what that logic's going to be, but without actually programming your board. Okay, and then it comes out with its answer. It did its little thinking, and it correctly said, hey, you're going to get output that looks like an AND gate. That's what we expect. So neither of them are on, so the output's off. A is on, the output's off. B is on, the output's off. We have A and B, and the output's on. Great. So waveform, there you go. That'll be very helpful later on. All right, we're ready to program. So this is where I'm going to, again, refer to this My First FPGA write-up. This is going to show you how to program. It's different for every board. So this is specific to the DE10 Nano. We already compiled, so we have check marks on everything. Let's double check on that. Check marks on everything, looks good. I'm going to try and close this out quickly. We're going to do program device, so we'll click open. I like to go up to tools, programmer. That's where I like to go. And this loads up. No hardware connected. So I'm going to switch over to the tabletop view. I'm going to take the power cable. Make sure your micro SD card is removed. If you leave that in, right here, so the board is oriented like this, and if you turn it this way, there's the micro SD card slot. If you leave that in there, it's going to erase whatever design you try to program to your board. So I'll leave it on there for like 2 seconds, and then a watchdog timer goes off and erases your board. So remove that SD card so that it's not there. If you can't get this to work, just look closely at the My First FPGA from start to finish. That shows you the whole process of getting this thing programmed. Okay, supply power. And that's really what I'm going off of, and I'm just trying to show you that the steps are going to be the same every single time you want to put a design on your board. Bring in your USB cable and plug it into the one, the J13 if you want to look at the number on the board. But it's the one that's the USB and it's next to the power cable on this side. Plug that in. Okay, and then right click on your little Windows icon here and go to Device Manager and just verify that that did connect. Oh, my sound is muted, so that's why I didn't hear the USB connecting sound. But if I go, yeah, JTAG cables, there is our Altera USB blaster. So we're good to go. So I believe we'll go to hardware setup first on the programmer, hardware setup, and select our DE SoC. Oh wait, no. Over here where it says no hardware, select DE SoC. Close, and then I think auto detect. I'm going off memory, but this is all straight out of the. Okay, so I don't know which one to pick, so I'm going to refer back to this document, My First FPGA. I don't have everything memorized, but yeah, we just did this step. We did this step. And the first one, we want the first one selected. Let's see, am I paused? No, we're good. We're rolling. Okay, good. Go back to the programmer. Yeah, first one selected, click OK. And say yes. Okay, and then this is our FPGA, the 5CSE-BA6. So we're gonna click on File here, and then we're gonna go to Output Files, and we need our SOF file. We'll click Open. That file was created when we compiled, so that's gonna have our, the code, the machine code that's necessary to do the programming of the FPGA. You could think of it that way. Okay. We're going to click this checkbox for Program Configure, and then we're going to click the Start button. And I'm reading those instructions right there. And it programmed. So now let's go ahead and switch over to the tabletop. And I'm going to flip this switch. Did it program? Flip this one. There you go. So right now I have switch 0 on, switch it off, and so the LED does not light up. And I have just switch 3 on. If I do switch 0 and not switch 3, the LED does not turn on. But if I have switch 0 and switch 3, it turns on. And so that is basically the whole process of creating a design. And this time we did it using the pretty pictures, the block diagram, and how you're gonna basically test it out, make sure it's looking good. Do the pin assignment. We saw how to do that live. That it really is the process. You just kind of flip through the schematics until you find your little pin code, type it in on the pin assignment, and yada yada yada. You saw the whole thing. You were there. This is how it's done. So from here, we now know enough to start doing more advanced, logic circuits. We're going to do combinational circuits. We'll get into sequential circuits. I think I want to get into MIPS. There's a lot of things I'd really love to get into in this tutorial series. So thanks so much for watching, and I'll see you in the next one. Take care.